In this video, we were going to be talking about different applications of an OpAmp. As we discussed earlier, OpAmps are basically devices that are made out of many transistors, and in this session, we're going to use the ideal OpAmp model to analyze this circuit. And if you recall, the ideal, as soon as somebody says we've got the ideal OpAmp, basically we are applying three rules. So when we have ideal OpAmp model, then we can simply assume that the gain is equal to infinite, so we can have as large a gain as we possibly want without running to the physical limitations of an OpAmp. Vp is equal to Vn, so the voltage on this side is equal to that side, and then Ip is equal to In equal to 0. So these are the three rules we have. So we're going to use what we've learned here to go ahead and build some sample applications of OpAmps. OpAmps could be inverting amplifiers. Amplifiers basically are devices that grow and shrink the voltage for you if you like to. You amplify them as gain or shrink it. And the summing amplifier basically allows you to have multiple things, multiple voltages coming together and get added. And then we have non-inverting amplifier, just like the inverting amplifier, but your output would have the same sign as your input. And of course, difference amplifier allows you to do subtractions. So we're going to do, these are four very common applications or types of amplifiers we can build with the OpAmp. And in this video, we're going to go through and build each one, kind of walk through it with just general variable resistors and all that, and just see how the whole process works out. Okay, so we're going to start first with the easiest one of the group, which is basically the inverting amplifier. And once we work out the solution, hopefully you'll see why this is called an inverting amplifier. So as we talked before, this is Vp, and then Ip is going to be the current that goes in here. And as we mentioned before, solving these problems is the easiest way to solve this problem is KCL, node voltage method. So, and then typically when we do these things, because we don't know what I out is and we don't really want to learn it, usually we don't write this particular node, even though you could consider that node. And when we say V of out is equal to, comes out here, what we are saying that V of out with respect to a reference point. Now, as we mentioned, as you see here, you have basically one node, which is here. This is really not an essential node. The only essential node is here, and of course the reference is essential node. So to analyze this inverting amplifier configuration, we only need to write one KCL at Vn, and that would basically be Vn minus Vs divided by Rs. That's this resistor here, and plus, and that's a current going this way, plus In plus Vn minus V out divided by Rf. This resistance is called the feedback, and notice the feedback resistance always goes from the output to the negative side. Remember, the gain is infinite, and this is slowing the gain, reducing the gain. Its job is not let the output voltage grow too big. So if I do this, then because this is an ideal OpAmp model we are using, we have to basically say that In is equal to Ip equal to 0, and Vn is equal to Vp. In this particular case, we also see that Vp is connected to ground, so Vp is equal to 0. So if we were to do that, we will see we can rewrite this whole set of equations and end up with basically this going to 0, Vn is 0, so we'll end up with Vs over Rs minus, when we take the V out onto the other side, Rf. So if we do a little bit more cleanup, we'll see that V out is equal to minus Rf over Rs Vs. Oh, so that's pretty interesting. That's a nice result that we can take a look at for the inverting amplifier. So if we look at this one more time and make it smaller so we can see everything. So if you look at this, now you'll see that this is the reason it's called an inverting amplifier is because it's got an output is a negative of the input. You see that? And notice what the gain is. The multiplier is the ratio of this resistor over this resistor allows us to determine what would be the output. Okay, so let's say if this was a 10K and this was 1K, then the gain would be 10. So whatever the input is gets multiplied by 10, and that becomes the output inverted, of course. And that's where the inverted amplifier names comes from. So let's go down. Let's go down and take a look at the next one. The next one is called a summing amplifier. More or less the same thing. There's really not much going on here. If you look at the summing amplifier, you got voltage A, voltage B, voltage C coming in, and it's pretty much going to work out. We'll show how it all works, but it's basically going to end up VA is going to be multiplied by the ratio of RF over RA, and then VB is going to be multiplied by RF over RB, and then VC is going to get multiplied by RF over RC, and sum of all that becomes a V. That's sum of that becomes V out, and that's why they refer to this thing as a summing amplifier. So let's do that. So again, if you look at that, V out is from here to a reference, and the only essential node we have here is this one. So we only have to write one equation. We write the KCL, add Vn, and that would be basically Vn minus Va divided by Ra plus Vn minus Vb divided by Rb, and all the currents, plus Vn minus Vc over Rc plus Vn minus V out over Rf, and all of that is 0. Again, much like we've talked about before, these are ideal OpAmp model. And since an ideal OpAmp model, as we talked before, Vp is equal to Vn. And since Vp is connected to ground, that's equal to 0. And of course, I didn't even write In because In is equal to 0, so I won't even write it. So that means all of these go away. See that? So if we clean this up, we'll find out that the V out is equal to minus Rf over Ra, Va minus Rf over Rb, Vb make it a little smaller so I can kind of show the rest of this, and then minus Rf Rc Vc, and you notice that these are the gains, Rf over Ra, as we talked about, and all that. Now, it's really important for both cases. I forgot to mention in the previous case, but you always got to make sure that V out is less than or equal, is greater than or equal to minus VEE, and is less than or equal to VCC. If it tries to go over that, it's going to be, if it tries to go over VCC, it's going to saturate at VCC. If it tries to go below it, it's going to go below that. So this quantity has to be in that category. And just before I forget, that same thing has to be true for the previous previous configuration. That's true always. Okay. Now another one is non-inverting, is kind of getting more or less very repetitive of what we are doing, but let's go ahead and, for completeness, let's go ahead and do this one as well. Again, the only note is this one. We usually don't write this one because it adds one unknown and one equation, so it really does not help. So if you do this one, this is called a non-inverting amplifier, and we'll see why that is called non-inverting amplifier. Notice even though input is coming on the positive side, the feedback always goes to the negative side. Never a case where feedback goes to the positive side, so remember that. Okay, so we're going to do a KCL at Vn. If you do a KCL at Vn, we're going to have Vn minus 0 divided by Rs plus Vn minus Vout over Rf. And we may not write it, but let's put it in this way to be complete, and then you got an In. But again, you've got a case where you have an ideal OpAmp, and because we have the ideal OpAmp model, we know that Vn is equal to Vp. So that tells us, although at this point we cannot necessarily say Vp is 0. As a matter of fact, we know that Ip is equal to In equal to 0. So if the 0 current is going, voltage drop here is 0 volt, because I times R is 0, which means Vp is equal to Vg. So Vp is equal to Vg, which basically says Vn is also equal to Vp. So Vg. So if I take that and plug it in here, this becomes Vg, this becomes Vg, this becomes 0. And now what's going to happen is my Vout equals to Rf over Rs times Vg. Notice this is just like the inverting amplifier, except the sign here is positive. So that's why this is called a non-inverting amplifier. Again, you have to make sure that this output is less than or equal to VCC, the bias, positive bias, and minus VEE, because if it tries to go below VEE, it's going to be cut off at that point, and if it tries to go above VCC, it's going to be cut off there, saturated at that point. All right, we got one more to do, and then we are pretty much done with all the common types of amplifier, and this one is difference amplifier, and is a little more involved in dealing with it, but not too bad, not too bad. So in this particular case, I've got an essential node here, I've got an essential node here. Again, really pay attention that the output is always connected to the negative side, but this time we got two input, A and B, each going to a different one. The idea is that this thing is going to subtract VA from VB, amplify it, and kick it back out as an output. So let's see if that's the case. So we've got the reference, we've got Vn, so we have to write two KCL. The first KCL we're going to write for Vn, and that's going to be Vn minus minus Va, what Ra, divided by Ra plus Vn minus, actually really should call this Rf. That's usually the name of it. We always refer to this as Rf, so let's call it Rf in this case as well. That's the feedback. So it's going to be Vn minus Vout over Rf, and that's equal to 0. Okay, great. Oh, of course there is this, but since it's an ideal model, I really don't have to put the In, which is the current here. And of course Ip, both of those are 0 because we have an ideal OpAmp. And then we're going to do a KCL at the node Vp, which tells us Vp minus Vb over Rc plus Vp over Rd, and then all that is equal to plus Ip, of course, equal to 0. Now, as we talked, as we were saying, all these are done under an ideal OpAmp model, which tells us that Ip is equal to In equal to 0, and Vp is equal to Vn, but not necessarily 0. In this case, it's not. So what's going to happen is that this is going to get cleaned up to 0. This is going to be 0. And we'll end up with two equations there. If you notice, from here we potentially could find Vp, if you like, from this equation down here, we will find that if VP is factor VP out, it would be 1 over RC plus 1 over RD times VP, and that whole thing is equal to VB over RC. So we clean this up. We got a VP from here that is equal to VB over RC times 1 over RC plus RD plus 1 over RD. Move a little bit higher, and then we can take that, plug it back into the first equation, because VP now we know is equal to Vn. We'll plug it back there, and we will clean it up and find the equation. So what in the end is going to happen, and I'm not gonna finish this. Don't want to make this video too long, but you can kind of follow this through. Take the Vn, plug it up here, and find the equation for V out. That's going to be an equation in terms of VB and VA and all of that. And this, then you also got to make sure that it stays less than VCC always and larger than VEE minus VEE in order for it to be not saturated and not cut off in the linear region. So just a recap of what we have done so far is that we started, this is kind of showing us the different ways we can connect amplifier, and these are not the only way. You can design whatever you want for yourself and be able to analyze it with ideal OpAmp. Surprisingly, in the DC environment with the resistive circuit, OpAmp's ideal OpAmp results are very, very close, within a few percentage points of the actual performance in a circuit. So that's really awesome that you can use this very simplified ideal OpAmp model and predict how the circuit will behave in actual world.